Okay, so here's how I want to do this. These two limits are really important. And I don't want to go through the squeeze theorem way of proving these two limits. They both, I just don't think it makes anything clear for anybody as far as how to use these things. So what I want to do with you is I want to plot these two functions and use the plot of it to establish what the value of the identity is. So I'm going to do that by bringing up my graphing calculator. So I'm going to clear my graphing calculator. So I'm going to go into y equals, and I'm going to clear that one, and I'm going to type in the expressions that I have. I'm going to type in what I have over there. Okay, and I'm going to go zoom 6 for the standard, and I've got a nice view of my function. Your vertical height might be different from mine. This one has a few different features, but it's right in the video, and that's what I want from this program right now. So the limit will exist if the function is well defined. So I should be able to zoom in, and I know you can't pinch and zoom on yours, but I should be able to zoom in, and it should just look nice and like go to a single value. And as I pan around and use the trace function and go left and right on it, I'm watching my y values, and it's pretty darn clear that this limit is equal to 1. So there's my graphical proof of the value of this limit. This limit is 1. Note also that this is an indeterminate form of the form 0 over 0. So let's do the same one for this. It's an indeterminate form because cosine of 0 is 1. And so I want you to use your calculator and tell me what the value of this limit is. One thing that I note here is that my calculator is calling it x, but in the limit it's called theta, and that does not matter. The name of the variable is arbitrary. I'm going to go zoom 6. Hopefully this is about what you're getting. And I already, so this calculator here does some like nice evaluation stuff for me. So it's showing me that I have x equals 0.002, and that generates a function value of 9.96 times 10 to the minus 5th. And if I zoom in on this, there's nothing weird happening here. Letters and okay. Except for their poorly implemented pinch to zoom. Okay. So what do you think? Indeed, I agree. The value of this limit is 0. And we established those both graphically. Sine of theta over theta around 0 looked like that. And it went to y equals 1. And the 1 minus cosine of theta over theta went to y equals 0. And again, I don't really care what's happening outside of the view that I show here. Like what's going on out here and out here, those don't influence the value of the limit because it's a purely local property. So I'm going to take these two identities now, and I want to use them to compute some values of some limits. So I've got two example functions out on my screen right here. One uses x, one uses theta. The name of the variable doesn't matter whatsoever. So I want to write that down because I don't think I've written that down yet. The name of the variable is completely arbitrary. So let's establish two facts. I know that the limit as, I'm going to call it h now because the name of the variable doesn't matter. Limit as h approaches 0 of sine of h over h equals 1. And the limit as h approaches 0 of 1 minus cosine of h over h equals 0. Those are my two facts that we established from the previous screen. And so we're going to use those on these two problems. So one thing that you should notice about this problem, which we're going to work on first, is that we get a mismatch in terms of the coefficient right here. So get that coefficient mismatch. So what I'm going to do is I'm going to introduce a 9 in the numerator. So I'm going to write that this is equal to the limit as x approaches 0 of 9x over sine of 9x. And you should be troubled by what I just did because it is multiplied by 9. And I'm not allowed to just do that. That'll scale the value of the limit by 9. And so I've got to also put 1 down there. So what I did was I multiplied by 9 over 9, which is just equal to 1. And I can multiply by 1 all I want. Next, I'm going to factor this one out. So I'm going to write this as 9 times the limit as x approaches 0 of 9x over sine of 9x. And now we got a little logical leap to make right here. This is one I want to work through with you. So note that as x goes to 0, 9x also goes to 0 because I have x going to 0. And so even though I'm scaling it by 9, the fact that x is going to 0 drags 9x to 0 also. And so this part here is going to 0 and this part here is going to 0. And so in order to make that clear, what I'm going to do is I'm going to rename 9x equals h. And note that as x goes to 0, h goes to 0. So I'm changing variables. I'm doing a substitution here. So that this is equal to 9 times the limit as h goes to 0 of h over sine of h. That's the logical leap that sometimes gets people in this problem. Now, one thing that I want you to notice about this function here is that it's the reciprocal of the one in the identity that we have right there. So I think we should add another fact to our list of facts. The limit as h goes to 0 of 1 over sine h over h is equal to, let's see here. So I have the limit of the reciprocal. This is a limit law. This is a limit of a quotient. This is equal to 1 over whatever the value of this limit here happens to be, which is 1, which is just equal to 1. I can reciprocate a function and I get the limit is the reciprocal. So this is just equal to 9 times 1. So this is just equal to 9. And I'm done. I would encourage you to get out your graphing calculator and take a look at the function that we solved here. Let's do zoom 6. Wow. Oh, what did I do wrong? Oh, I know what I did wrong. I know what I did wrong. Look at the problem. So it doesn't go to 9. Look at this. Do you see my problem on the left here? It's right here. It's when I factored this out. Somehow my 9 in my denominator made it into the numerator. Oh, geez, what a mistake. Oh, geez. I love the graphing calculator as a tool to check my work. I never claim to be perfect. I never claim to not make mistakes. I make the same mistakes that you do. I make the exact same mistakes that you do. So I mean, this is a mistake I would expect someone to make when doing these problems. And so the like sidetrack answers that you'll find in our quizzes and stuff like that, quizzes and exams, will often offer those as answers because we want to check that you really understand it. And if only one is clearly correct and everything else is just completely bogus, then it's not really testing what you know in such a strong way. So here I made a mistake. I made a mistake because I failed to bring my 9 down into the denominator. And that caused me to get the wrong answer, but I was able to catch it by plotting my function. Do you see the power of the graphing calculator?